I want you to just take a second and look around the room you're in right now. Like literally right now.
Yeah, just take
Look at the, that sleek brushed metal frame on the window you might be staring out of. Or think about the incredibly complex finned heat sink that's humming away inside your laptop.
Right, keeping it from completely melting down while you listen to this deep dive.
Exactly. We are surrounded by these perfect, flawless, modern metallic shapes. And we take them completely for granted. I mean, I know I do.
Oh, for sure. We all do.
But every single one of those precision-engineered objects started its life as a humble, heavy, seemingly unremarkable block of metal.
It is so easy, to look at a finished product, say like a lightweight aerospace component or a massive building facade, and completely disconnect it from the raw material it was born from.
Right.
We tend to focus entirely on the design, the assembly, the final polish. But the reality of manufacturing is, it's much less glamorous and much more foundational.
And that is exactly what we are getting into today. We've got a fascinating source on the table. It's a comprehensive manufacturing guide from Eleanor Industries,
Which is a premier aluminium extrusion supplier based in India.
Right. And our mission for this deep dive is to decode this seemingly simple world of aluminium ingots. Because it turns out choosing a block of raw aluminum is not just some basic procurement checkbox on a spreadsheet.
No, not at all.
It is an absolute masterclass in precision engineering.
Okay, let's unpack this. Where do we even begin with a block of metal?
Well, we begin with the why. The reason raw material selection is so critical is that it is the absolute foundation. It dictates the structural integrity, the surface finish, and, the thermal performance of the final product.
So it's everything, basically.
Exactly. If you get the raw material wrong at step one, no amount of brilliant engineering or million-dollar machinery downstream is going to save your product. It's a cascading effect of failure. Wow, okay. I want to understand the physical journey here, then. The guide talks heavily about aluminium ingots. And my understanding is that an ingot is basically just a cast block of refined aluminium, right?
That's right.
But how does, dirt from the ground become the metal that a company like Eleanor Industries uses?
The transformation is actually quite brutal, honestly.
Huh.
You start by digging bauxite ore out of the ground, which essentially looks like a reddish clay.
Okay.
And that clay is chemically refined into this fine white powder called alumina.
Just a powder.
Yeah, just a powder. Then you have to blast that powder with massive, continuous amounts of electricity in a smelting pot. This strips away the oxygen, leaving you with pure liquid aluminium.
Wow.
And then that liquid is poured into molds to cool, creating those solid blocks or, ingots.
But in the extrusion industry, they don't just shove a rectangular brick into a machine, right? The guide mentions they take these ingots and cast them into billets.
Right, so a billet is a massive, solid, cylindrical log of aluminium.
Like a metal tree trunk.
Pretty much. And the extrusion process itself is actually quite intuitive. You take this cylindrical log, you heat it up in a furnace until it's highly malleable, but not quite a liquid. It still holds its shape.
Okay, got it.
And then you force it under immense hydraulic pressure through a shaped steel opening called a die.
It sounds like the world's most aggressive, high-stakes, Play-Doh fun factory.
Honestly, the physics are remarkably similar.
Yeah.
But the catch is that the quality of that metallic Play-Doh, the billet, determines absolutely everything.
Right, because of the pressure.
Exactly.
Yeah.
If there are microscopic inconsistencies in the log, they're going to be massively amplified when you try to squeeze it through a complex die shape.
That makes sense.
And this forces a manufacturer into their first major decision, choosing between primary and secondary ingots.
Ah, okay.
Primary ingots are produced directly from that bauxite refining process we just talked about. They offer extremely high purity levels, typically like 99.7% pure or even higher.
Okay, and secondary?
Secondary ingots, on the other hand, are made from melted down recycled aluminium scrap.
Okay, so wait. The push for sustainability is huge right now, right? Every company wants to be eco-friendly.
Sure, yeah.
So if secondary aluminium is highly cost-effective and it keeps scrap out of landfills, why would any modern manufacturer ever demand primary aluminium? It's like making a soup, right? Primary is using farm-to-table fresh ingredients, and secondary is making a new stew from last week's leftovers.
That's a great analogy.
So why demand the fresh stuff if the leftovers are cheaper and better for the planet?
Well, if we connect this to the bigger picture, the answer comes down to unforgiving mechanical reality. It's a bit like trying to build a perfectly balanced, high-end mechanical watch using gears you salvaged from 3 different broken clocks.
Oh, man.
You might be able to make the pieces fit together, but you cannot guarantee how the microscopic friction is going to behave over time. Secondary scrap intrinsically comes with trace elements.
Like tiny bits of other stuff.
Yeah, tiny bits of other metals mixed in from whatever its previous life was.
Yeah. And those trace elements cause physical problems.
Massive problems. Even a fraction of a percent variation in the chemical composition can cause the metal to physically tear and fracture while being pushed through that extrusion die.
Just from a fraction of a percent.
Yes, or it can cause microscopic surface defects. When a manufacturer needs tight dimensional tolerances for an aerospace part, or a truly flawless mirror-like surface finish for a luxury architectural profile.
Recycled scrap just can't cut it.
Right, recycled scrap just cannot guarantee that level of purity yet.
That makes perfect sense. I mean, you can't have a luxury hotel facade looking like a patchwork quilt because somebody wanted to save a few bucks on recycled scrap metal.
Exactly.
So let's assume we are using that pristine primary aluminum. The Eleanor Industries guide keeps hammering on this specific category called the 6000 series alloys. Why is this specific series considered, like, the holy grail for extrusion?
Well, pure aluminum on its own is actually quite soft and weak. Yeah, to make it useful for construction or manufacturing, you have to add specific alloying elements. The secret sauce of the 6000 series is the precise balance of 2 elements, magnesium and silicon.
Okay.
By tweaking the exact ratios of those 2 additions, you can completely alter how the metal behaves mechanically.
The source breaks down a few specific variations. Can you walk us through the heavy hitters in this 6000 series menu?
Sure. The most common one you interact with is 6063. This is the architectural standard.
Okay.
If you are looking at a sleek window frame, a sliding door system, or a modern curtain wall on a skyscraper, you're probably looking at 6063. Its primary advantage is what we call an exceptional anodizing response.
Okay, I see that term constantly. What is anodizing actually doing to the metal?
So anodizing isn't just a coat of paint that sits on top of the metal.
It's not.
No, it's an electrochemical process. You submerge the aluminum in an acid bath and pass an electric current through it. This forces the metal to grow a highly controlled, incredibly hard, and porous layer of aluminum oxide.
So it's basically what? Controlled rust. Essentially, yeah. It's controlled rust on its own surface. 6063 responds beautifully to this, creating a flawless, protective, and highly decorative finish.
Okay, so 6063 is for the beautiful finished look. What about the others?
Then you move to 6061 and 6082. These are the heavy lifters.
The strong ones.
Right. They have a higher concentration of alloying elements, which dramatically increases their tensile strength. These are used for industrial machinery frames, heavy automotive parts, structural components where, failure isn't an option.
Gotcha.
And sitting right in the middle is 6060, which offers a moderate balance. It's stronger than 6063, but with a better surface finish than 6061.
Now, here's where it gets really interesting, though. 6060 is this nice, versatile metal. But it makes me wonder, if 6061 is the absolute strongest one on the menu, why not just over-engineer everything?
The classic engineering trap.
Right, like why not build every window frame out of industrial strength 6061 and just never worry about it breaking? What's fascinating here is that in the world of metallurgy, structural strength almost always trades off with aesthetics and formability. You simply cannot have it all.
Oh, really?
Yeah, because 6061 has that higher concentration of magnesium and silicon to give it structural strength. Its internal atomic grain structure is inherently different and much denser.
So it fights back against the finishing process.
Exactly.
Yeah.
If you use structural 6061 to build a decorative curtain wall and you tried to apply that beautiful anodized finish to it, the dense grain structure would cause the finish to look dull, gray, and littered with structural blemishes.
Oh, yuck.
Yeah. Furthermore, 6061 is physically much harder. Trying to push it through an extrusion die requires immense pressure, which wears down the expensive steel tooling much faster.
Which costs more money.
Way more money. And it severely limits how thin or complex the extruded shapes can be. You absolutely have to match the ingot's specific chemical recipe to the end application.
Okay, so we have the right recipe. We've perfectly balanced our magnesium and silicon for the job. But looking at the source, it seems like getting the main ingredients right isn't enough to save you.
Far from it.
The text goes into terrifying detail about microscopic trace elements, these invisible impurities that can completely ruin an entire production run. What are we actually worried about here?
We are talking about elements that are present in mere fractions of a percent, yet their impact is disproportionately destructive. The big three offenders mentioned in the text are iron, copper, and zinc.
Okay, iron first.
Right. Let's take iron. Elevated iron reduces ductility, meaning it makes the metal far more brittle and prone to cracking under stress. But more dangerously, it destroys thermal performance.
Wait, how does a tiny fleck of iron ruin thermal performance?
Well, if a manufacturer is building aluminum fins for an industrial heat exchanger or, a laptop heatsink, the whole point is for the aluminum to pull heat away from the electronics quickly.
Right.
Iron literally acts as an atomic roadblock to thermal conductivity. The heat hits the iron atoms and just stalls out.
Oh, wow.
Yeah. So the equipment overheats, the end user blames the electronics brand, and the root cause was literally a fraction of a percent of iron hidden in the raw ingot months prior.
That is wild.
Mm-hmm.
And the guide also mentions copper impairs corrosion resistance, meaning the metal will degrade much faster if exposed to the elements.
Correct.
And zinc ruins weldability, making it impossible to reliably join two pieces together. It reminds me of salt in baking.
Oh, that's a good comparison.
Right. If you are making a delicate pastry, a tiny pinch of salt elevates the entire flavor profile. But if your hand slips and you drop in a handful of salt, it doesn't matter how high quality your flour was or how perfectly you baked it, you have ruined the entire batch at a molecular level.
Exactly.
But that leads to a huge operational question. These elements are invisible. How does a manufacturer actually know what invisible contaminants are hiding in their metal before they melt it down and ruin their tooling?
This is exactly why the Eleanor Industries Guide emphasizes the absolute necessity of a batch-specific spectrochemical analysis report.
Spectrochemical analysis, what does that actually look like in practice?
It's essentially a chemical fingerprinting process. They take a physical sample of the metal from specific delivery, zap it with an electric spark, and analyze the specific wavelengths of light that the vaporized metal emits.
Wait, light?
Yeah, light. Every element emits a unique light signature when zapped. This tells them exactly, down to the thousandths of a decimal point, what elements are present in that specific batch.
That is incredibly sci-fi. But the guide doesn't just talk about the villains, it talks about the heroes, too. To fight physical inconsistencies in the metal, it mentions a solution called grain refinement, specifically using titanium boron master alloys.
Yes, grain refinement is crucial.
But how does adding more metal fix the metal?
This goes back to the physics of how liquid turns into a solid. When liquid aluminum cools and solidifies in a mold, it crystallizes. If you just let it freeze naturally on its own, those crystals or grains grow massive, irregular, and jagged. When you later try to push those massive, jagged grains through an extrusion die, the metal flows inconsistently, causing surface tearing.
Ah, so what does the titanium boron do?
Adding a titanium boron master alloy to the liquid metal before it cools is, well, it's like seeding clouds for rain.
Oh, I like that visual.
Thanks. The titanium and boron particles act as millions of tiny, artificial starting points nucleation sites for the aluminium crystals to grow on.
So it forces them to be smaller.
Precisely. Because there are millions of these tiny seeds, the aluminum is forced to form a very fine, tight, and incredibly consistent microscopic grain structure.
Wow.
This fine structure makes the metal flow predictably like warm butter, reduces wear and tear on the dies, and dramatically improves the final surface finish.
Okay, so we've added titanium to fix the grain, and we've kept the iron out. Our chemistry is flawless.
Perfect chemistry.
But looking at the source, it seems even with perfect chemistry, the metal still fails if we don't handle the physics of how it cools down. They talk about a process called homogenization.
Homogenization is the crucial step that completely distinguishes premium suppliers from corner-cutting operations. It is a highly controlled, prolonged heat treatment applied to the cast billets after they have solidified.
Okay.
The goal is to take all those alloying elements we just talked about, the magnesium, the silicon, and redistribute them completely evenly across the entire cross-section of the log.
You know, when I was reading about homogenization, the image that immediately came to mind was ordering an iced coffee.
An iced coffee.
Yeah, hear me out. If you pour a packet of solid sugar into a freezing cold iced coffee and just let it sit there, all the heavy stuff, the sugar just sinks and clumps uselessly at the bottom.
Right, it doesn't mix.
Exactly. The top of your drink is bitter, the bottom is pure sludge. But if you agitate it, if you treat it right and mix it, the sugar dissolves and distributes evenly, so every single sip tastes exactly the same.
That is spot on. And just like your sugar clumping at the bottom of the cup, When a massive billet of aluminium cools after being cast in a foundry, it doesn't cool uniformly.
Because the outside is touching the cold mold.
Exactly. The outside surface touching the mold cools much faster than the molten core. Because of this steep temperature gradient, the alloying elements get pushed around and tend to segregate and cluster in certain zones of the log.
Which is bad.
Very bad. If you take that unhomogenized clustered log and shove it through an extrusion press, the metal will flow unevenly. You will get wild variations in mechanical strength from one end of the extruded profile to the other.
So what does the homogenization actually do then?
Homogenization uses prolonged, controlled heat in a furnace to essentially stir those elements back into a perfectly even distribution at the atomic level without melting the log entirely.
But wait, if homogenization is just putting the solid metal into a giant oven for a few hours, it's totally invisible to the naked eye.
Yep, completely invisible.
You can't look at a billet sitting on a pallet and instantly know if it's been homogenized or if the magnesium is like clumping in the center. How do you verify an invisible process?
This raises an important question, and it bridges our conversation directly from the science of metallurgy to the harsh, practical realities of the supply chain.
Right.
Because these treatments, spectrochemical analysis, grain refinement, homogenization, they are largely invisible until the metal is already inside your expensive machinery. Buying ingots is ultimately a high-stakes exercise in trust.
It sounds terrifying.
It can be. Vetting a supplier is just as technical a process as vetting the metal itself.
The guide actually lists a series of massive red flags to watch out for. First up, generic grade certificates instead of batch-specific ones.
Yeah, if a supplier hands you a piece of paper that says, this is 6063 alloy, trust us.
Yeah.
But they cannot provide that spectrochemical lab report for the exact delivery truck sitting in your loading bay runaway.
Just don't accept it.
No.
Another glaring red flag is unusually low pricing, which sounds great to a purchasing department, I'm sure, but what's actually happening there?
In a global commodities market, raw material prices are generally fixed. If a supplier is significantly undercutting the market rate, they're almost certainly cheating the alloy profile.
By using scrap.
Most likely, yeah. They are likely blending heavily polluted, cheap secondary scrap into the melt to make weight, and just hoping you don't check the chemistry too closely before you use it.
The guide also mentions physical defects to look out for on the outside, specifically shrinkage cavities and cold shuts. What causes those?
Those are visible signs of incredibly sloppy casting practices at the foundry. A cold shut, for instance, happens when pouring liquid metal into a mold from two sides.
Okay.
If the metal is cooling too fast, by the time those two streams meet in the middle, they're too sluggish to actually fuse together.
Oh, so they just hit each other.
They just smash into each other, leaving a hidden physical crack inside the solid block. If you see those on the surface, the inside is guaranteed to be a disaster.
So what should a manufacturer demand instead? The text lays out some hard requirements. ISO 9001.2015 certification and compliance with standards like ASTM B2211 or EM573.
And those standards aren't just acronyms on a brochure. ASTM B221 requires the finished metal to undergo actual physical torture tests.
Torture tests.
Yeah, literally stretching it until it snaps to measure exact tensile strength and testing its yield limits to ensure it behaves predictably under stress.
So what does this all mean? For me, it highlights the absolute false economy of bargain hunting for raw materials.
Oh, absolutely.
Let's say a purchasing manager decides to save a few cents per kilogram by going with a shady supplier offering unhomogenized, loosely certified ingots. They might look like a financial hero on a spreadsheet for, like, a week.
Right, until it hits the floor.
Exactly. When those ingots get pushed through the press, they snag and destroy a $10,000 steel extrusion die. Or worse, the parts get made, they get shipped to an automotive plant, and they completely fail a structural stress test on an assembly line.
It's a nightmare scenario.
Those few cents saved up front just cascaded into millions of dollars, lost and rejected parts, ruined machinery, and permanently shattered client trust.
That's the reality of it. A competent supplier must fundamentally understand downstream extrusion requirements. If a supplier's attitude is simply, here is your heavy block of metal, our job is done, and they don't care how that specific metal behaves inside your specific hydraulic press, they are a liability.
Not a partner.
Right. The relationship between the ingot supplier and the extrusion manufacturer has to be entirely symbiotic.
It is incredible to think about the journey we just mapped out. I mean, we've gone from digging raw bauxite clay out of the earth to blasting it with electricity to carefully balancing a magnesium silicon recipe to policing microscopic iron villains.
Don't forget seeding the liquid metal.
Right. Seeding the liquid metal with titanium boron to manipulate crystal growth, and finally baking it in a homogenization oven so the internal atomic structure is perfectly calm and even. All of this happens before the metal ever gets turned into an actual product that we use.
It completely recontextualizes the physical objects we interact with on a daily basis, doesn't it?
It really does. The next time you grab the handle of a sleek aluminum door, or, you run your hand along a perfectly finished window frame, I want you to remember this deep dive.
Yeah.
You aren't just feeling a piece of metal. You are feeling the physical, real-world result of spectrochemical analysis, of master alloy grain refinement, and of a highly disciplined supply chain that demanded absolute perfection at the atomic level. It is a quiet, invisible history of engineering that makes our modern world possible.
It is a triumph of modern manufacturing, certainly.
Mhm.
But, as we look toward the future, this delicate balance of chemistry and purity brings up a rather pressing complication.
Oh.
We started this discussion by comparing primary pure aluminum with secondary recycled scrap. As the world rightfully pushes harder and harder for sustainability, we are relying more heavily on that global pool of secondary scrap.
Right.
But think about what we are throwing away today compared to 20 years ago.
Mm,
We aren't just recycling simple aluminum soda cans anymore.
that's true.
We are recycling incredibly complex new alloys from discarded modern tech smartphones, electric vehicle chassis, advanced aerospace components. This modern scrap is teeming with exotic trace elements that were never there before.
Oh, I didn't even think about that.
So the question is, will our metallurgical ability to filter out complex impurities keep pace with the increasing complexity of our garbage? Or are we hurtling toward a recycling bottleneck where our secondary scrap pool becomes simply too polluted with exotic tech waste to ever use for the high-precision manufacturing of the future?
Wow. That is a heavy, heavy thought to leave off on. We desperately want a green future, but our high-tech trash might actually be poisoning the well for the precision engineering we need to build that future.
It's definitely something we'll have to reckon with.
Fascinating. And on that note, we'll wrap up this deep dive. Go take another look at that window frame, and we will catch you next time.